Good afternoon. Here we are back at buffers. I know we already talked about the 5 important points on a weak acid base titration, but I thought I'd review it again. Places or things that you want to look at for titration curves is 1, the pH before the titration begins. Number 2, the pH on the way to the equivalence point, and we know that that's the buffer area. The third point is the pH at the midpoint of the titration, or we also call that the half equivalence point. If we're using a weak acid and a strong base, or vice versa, the H plus is going to equal the Ka, or we could say the pH is going to equal the pKa. We just take the negative log of both the H plus, take the negative log of Ka, and you'll get pH equals pKa. Number 4, the pH at the equivalence point. At that point, all the acid in the base has been neutralized. So if we want to calculate the pH, we are going to calculate the pH of the salt. So you're going to need to use the hydrolysis reaction of the salt for the R on the rice table. And the 5th part, after the equivalence, we'll just take a look at the pH beyond the equivalence point. And here we can use stoichiometry with limiting reactant. So we're going to calculate the molarity of the excess and solve for pH or pOH. Let's get started with this problem right here with the hydrogen cyanide. It's a weak gas. Ka is 6.2 times 10 to the negative 10. Sorry, I just realized that this right here, that should be exponent. If we have a 50 ml sample of a 0.1 molar hydrogen cyanide and it's titrated with a 0.1 molar sodium hydroxide, calculate the pH of the solution at these points. So the first point is once we've already added 8 mils of the sodium hydroxide. So since we're using a weak acid with the base, we're going to use our buffer formula. And our buffer formula is, it's H plus equals the Ka times the ratio of the weak acid over the weak base. Now, remember, since we are adding sodium hydroxide, we have to go to moles. So we're going to convert everything over to moles. Okay, so I'm going to calculate my number of moles of acid. If I had my moles equals the number of milliliters, I'm going to keep it in milliliters, milliliters times the molarity, 0.1. So I'm going to have mole is going to equal to 5 millimoles acid. Okay? And I'm going to figure out how many moles of base I have. So again, moles is going to equal 8 milliliters times the 0.1 molar. So I have 0.8 millimole of base. Alrighty, so then what I'm going to do is I'm just going to plug everything into this, into the buffer formula. So H plus equals, since they already gave us the Ka, we don't have to do anything, 6.2 times 10 to the negative 10, and this is where we're going to do some addition and subtraction. Now we started off with 50 millimole of acid, so we're adding base to it, so we're going to subtract the amount of base, and that's in millimoles. Now in this case we didn't have any base to start off with because we're doing a titration, but then we're going to add base, and we added 0.8 millimole. So my H plus concentration is going to be equal to 3.26 times 10 to the negative 9. And then you guys can calculate the pH. What do you guys need to do? Negative log of your H plus concentration. And if you're working it out with me, then you're going to plug this into your handy dandy calculator, and your pH is, got it? 8.49. Okay, very good. So now let's do the next one. Point along the way is the halfway point. Halfway point is the same thing as the half equivalence point. Right? And what did we say at the half equivalence point? At the half equivalence point, we said that the H plus concentration is going to equal the Ka. So we know that the H plus is going to equal Ka at 6.2 times 10 to the negative 10. That means my pH is going to be equal to 9.21. That was easy. You could have worked it out, and if you did, you would have realized that your weak acid to weak base ratio is 1 to 1. Or you could have just used the rule. Either or, whatever's easier. This is easier. Okay, and now the last point. Now here we are, it says we're now at the equivalence point. So we went back to our point, I can't remember what point it was, 3 or something like that, maybe 4, where we said, now once we're at the equivalence point, all the moles of acid and all the moles of base have been neutralized. So the pH of the solution is going to be the pH of the salt. So this is where we have to use the hydrolysis. But we have a couple things to consider. We know at the equivalence point the moles acid equals the moles of base, base, which equals the moles of salt. Okay? We also know the total volume of the solution. So total volume of the solution is going to be the 50 mils of acid plus 50 mils of base that we added. Now, how did I know we added 50 mils of base? I just did a little calculation. If I know that moles acid has to equal moles base, then just by calculation, I know that I have I have 5 millimoles of acid. In order to get 5 millimoles of base, I needed 50 milliliters because the molarity of NaOH is 0.1. Okay, what else do we need to know? I think that's it. And then we can go into our hydrolysis equation. So we know that the salt that's going to be produced is going to be the, if we have HCN plus NaOH, we're going to produce NaCN plus H2O. Okay, so what we're going to do is we're going to use that salt. And we're going to do the hydrolysis of the salt. So we know we have a strong base because we're using a weak acid and a strong base. It's listed up here in the problem. Hydrogen cyanide is weak, and we know that sodium hydroxide is strong. So in my hydrolysis equation, I'm going to have this one for my reaction. Okay. I know that since I'm using a strong base, I'm going to have OH. Okay. So then my Na is my spectator. So CN plus H2O is going to form the OH plus the HCN. So there's my reaction. So there's my R. Let's see, I'm going to need another page. Okay, so let me redo my R. CN plus H2O forms, that's my OH, and plus HCN. So since I have OH, I'm going to need to have my KB. And originally I was given Ka. So let's do the whole rice table first. Okay. Now, remember that my total volume of the solution was 100 mils. Okay? And our moles of acid equals moles of base equals moles of salt, so we had we had 5 millimoles. So if we have 5 millimoles divided by my total volume, which is 100 milliliters, I have 0.05 as my molarity for my salt. Okay? Now we can use this for my I. So CN, the molarity for CN, 0.05. Since it's initial, we have 0 for the OH and 0 for the HCN. The change is going to be 0.05 minus X. This is plus X, and this is plus X. So my equation is going to be 0.5 minus X, X, and X. Now, if we go back and we look at our OH, we know we have a basic solution. In our original problem, we were given the Ka equals 6.2 times, I think it's times 10 to the negative 10. Remember that? So, can we use the Ka here? Nope. Why not? Because we have a basic solution. So we have to convert Ka to Kb. You take 1.0 times 10 to the negative 14 divided by 6.2 times 10 to the negative 10, and you can get 1.61 times 10 to the negative 5. Negative 5. Okay? Alright, we're almost there. Let me get a new clean. Okay, so our equilibrium expression is going to be Kb equals x squared over 0.05 minus x, and our Kb, 1.61 times 10 to the negative 5 equals x squared, and we know we could neglect x, so I'm just going to neglect, cross multiply right here to get 8.05 times 10 to the negative 7 equals x squared. So x is going to equal 8.97 times 10 to the negative 4. And now this is going to equal my OH concentration. So if I want to calculate pH, I'm going to calculate my POH first. POH, negative log of your OH. So what are we getting? We're going to get 3.05. And so if I want pH, I'm just going to take 14 minus my POH, and I get 10.95. So, there you have it. This one was a nice little short recording. I think this is all you're going to need for your homework. So, hopefully you have everything you need by Sunday to get your homework done. And I will see you all tomorrow. Have a good day.